Hi folks, we're going to take a look at number 10 from page 206. So they want us to find the constants a, b, and c such that this cubic function has a local extremum at 211 and a point of inflection at 1,5. Okay, so the idea here is to hopefully create some equations that allow us to find these unknowns a, b, and c. So since we have three unknowns, we're going to need three pieces of information. And when you take a look, we actually have four pieces of information because we know there's a local extremum at 211. Now, because this is a polynomial, we know that that's going to have to occur when the first derivative is 0, since the derivative always exists. So we know that the first derivative is going to be equal to 0 because of this first piece of information. And again, there's a point of inflection at 1,5. So the second derivative, because it's a polynomial, has to exist. So if it's going to have a point of inflection here, it means the second derivative is going to be equal to 0 at 1. Okay? But if this is a local extremum and this is a point of inflection, these 2 points are actually on the function. So we actually have more information than we need. Now, the question is how to proceed on these. And usually you want to proceed with the simplest possible function, and that's not going to be the derivative itself. The function itself. Because what happens when you take the derivative of f? Well, the derivative of this constant is just going to be equal to 0. So when you're working with the derivative, you've actually eliminated one of those unknowns, leaving you with only two variables. And then, of course, when I take the second derivative, well, again, that c is also still not going to be there. I'm only going to be left with a and b. So that's how I'm going to start by working with the derivative and the second derivative. So take the first derivative, okay? So that's 3x squared times a, so 3ax squared plus 2x times b, so 2bx. And then, of course, as we said, the derivative of c is just equal to 0. Okay, and when we take the second derivative, we get x squared is 2x, so we end up with 6ax plus, and the derivative of x is 1, so we're just left the constant 2b. All right, so now I'm going to start inputting the information that I have. So I know that there's a local extremum at 2, which means that f prime at 2 has to be equal to 0. Again, remember what we said. We can only make that assumption because we know the derivative is going to exist, meaning the critical point can't occur when the derivative doesn't exist, which is also a possibility. So let's just put in x equals 2. So 2 squared is 4 times 3. So we have 12a plus 2 times x equals 2 is 4 plus 4b. And that's going to be equal to 0. And I'll divide both sides by 4 to make it simpler. So here we have 3a plus b equals 0. So we have an equation with a and b. So hopefully I can come up with an equation with a and b using the second derivative. So here, because we have a point of inflection at 1, we know that the second derivative at 1 has to be equal to 0. So if we input 1 here, what are we left with? We're left with 6a plus 2b is equal to 0. All right, so let's divide both sides by 2. We end up with 3a plus b is equal to 0. But when I look at this, I see it's the exact same information as the original one that we did with the first derivative. So this adds nothing new. Okay, but remember we said we had three unknowns with four pieces of information. It just turns out that two of those pieces of information gave us the same equation. So luckily, we still have the fact that 211 and 1,5 are points on this curve. All right, but with this equation here, I can simplify things because I can write b equal negative 3a. So that means when I create my equations with these 2 points, I can just replace b with negative 3a. All right, so let's do that. Let's try to create another equation here. So I have that f at 2 is equal to 11. So I'm going to stick 2 into my equation here. So 2 cubed is 8a. So I'll just write it out. So there you go. You can see that, 8a. 2 squared is 4 plus 4b. Okay, but remember, b is equal to negative 3a. So wherever I see a b, I'm just going to replace it by negative 3a. Okay, then plus c, and then that's going to be equal to 11. Okay, and just so that we can see the equation, I'll do the other one here. We also have that f at 1 is equal to 5. So let's replace 1 into this equation. This one's a little easier. It's just a plus b plus c. So a plus, but remember, everywhere we see b, we're just going to replace it with negative 3a plus c is equal to 5. All right. And now I've got two equations with these two unknowns here. Okay, so if I call this equation 2 and equation 3, So let's simplify here. So 8a minus 12a, so we have negative 4a plus c is equal to 11. And then here we have a minus 3a, so negative 2a plus c is equal to 5. So I'll just place this one underneath. Negative 2a plus c is equal to 5. Subtract these two equations so I can eliminate the c. And negative 4 plus 2 is negative 2a. The c's cancel out. 11 minus 5 is 6. So a is equal to negative 3. All right. So there we go. We found our a value. Now remember that our b value is just given by negative 3a. So b is just equal to negative 3 times a, which is negative 3. So b is equal to 9. All right, and the last one here for c, I can use either one of these equations. I'll use equation 3 here. So here I have negative 2 times a, which we just found was negative 3, plus c is equal to 5. So c is equal to 5. So this is 6. Negative 2 times negative 3 is 6. When I bring it to the other side, it's minus 6. 5 minus 6 is negative 1. All right. So we found our solution. Let's do a quick recap, because now I've actually done solutions for quite a few of these questions here. And it has to do with the function that's missing some information. Very often it's coefficients to a polynomial. And we use this information, such as points on the curve, that we can input to create an equation with a, b, and c in this case here. The fact that in this case we have a local extremum, so the derivative being equal to 0 at this point, or point of inflection, the second derivative being equal to 0. So the idea is to use all this information to eventually get enough equations that you can solve to determine the unknowns. All right, that's it for this one.